Hello. In this video, I will show you how to graph polynomial equations, including how to find end behavior, x-intercepts, local minimum and maximum, domain and range, and increasing and decreasing intervals. Let's get started. In our first example, it states, find the end behavior of this function. And our function is f of x equals x to the third minus x squared minus 6x. So, to find the end behavior, we're going to look at the exponents, which are here, here, and here, which is actually a 1. And we're going to find which has the highest degree. And in this case, it's the 3. It's the one that has the highest number out of those. And so, since this number here is odd, we're going to have a function that either, on a graph, will either look like this or like this. And that is because this number here is odd. So, since this is odd, the function will either look like one of these. And to find which of these is the answer, you're going to look at the coefficient of the term that has the largest degree. So in this case, in front of the 3 here, there's actually a 1. And so, since this number here is positive, there's no negative sign in front of this one, it means that we would want this equation here. If it happened to be, if this number here happened to be a negative x to the third, we would want this function here. But since it's not, and it's just an x, and it's positive, we want this function here. So, to write out the end behavior for this, it is f of x is going to, and this here would be negative infinity, since this is the same as y, and the y is going downwards, which is negative infinity. And then as x is also going to negative infinity. And also, f of x is going to infinity, which is positive, as x is going to infinity. So as this x here is going towards infinity, the y is also going up towards infinity. So that's how you would write the end behavior for this equation. Let's look at another example. For our second example, we're going to find the end behavior of this function here, which is f of x equals negative 2x to the fourth plus 4x squared. So first, as we did before, we're going to look at the exponents and see which one has the higher degree. And in this case, it's the 4, because 4 is larger than 2. And since this number here is even, unlike the last one which was odd, your function is either going to look like this, or like this on a graph. I can imagine if that was a graph. So there we go. So that's because this is even here. It'll either look like one of those. Now, to find which one of these is the actual answer, you're going to look at the coefficient again, and for in this case, it's a negative 2. So because it is negative, we want this graph here. Now, this isn't the way that the actual graph looks like for this equation, but it gives you a general idea of which way the graph will actually look when you plug this into a calculator or you actually solve it out and see how the graph looks. So, for this equation, we will have f of x going towards blank as x is going to infinity, and also f of x is going to blank as x is going towards negative infinity. So in this case, since the when x is going to infinity, which is this way over here, because this keeps going on forever, it's going towards negative infinity. And as x is going towards negative infinity, which is over here, the f of x, which is y, is also going towards negative infinity. So that's how you would find the end behavior for one of these functions. Now, to recap everything on end behavior, we're going to start up here. If the degree is even and a, which is the first term of the equation that you're looking at, if it's positive, then as f of x is blank, as x is going towards negative infinity, both of these are going to be positive infinity. And your equation is going to look something like this. If your degree is even and your a is negative, then both of these terms here are going to be negative infinity. And your equation is going to look something like this. For this one here, if the degree is odd and a is positive, then as x is going towards negative infinity, your f of x is going to be negative infinity as well. And as x is going to infinity, your f of x is also going to be infinity. And your graph is going to look something like this, which is going in the general direction of like this way up here, which shows that it's a positive. And if your degree is odd and your a is negative, then as your x is going to negative infinity, your f of x is going to positive infinity. And as your x is going to positive infinity, then your f of x is going to negative infinity. And your graph, I'm going to kind of write out my words here, is going to look something like this, which is going down in this general direction, which shows that it's a negative function. Now I'm going to show you how to actually graph a polynomial function. So this question asks, graph the function. Include the zeros, which are also known as the x-intercepts, the local minimum and maximum, domain, range, and increasing and decreasing intervals. For graphing this, we're going to use a calculator, and I'll show you how to use your calculator to plug this function in and get your actual graph. Now you can graph this using a calculator, such as this, by going to y equals, make sure you have everything cleared here. I'm going to use alpha y equals and bring up this, and we're going to plug in our equation since y is the same thing as f of x and our equation had f of x equals 1/2 x minus 4 cubed. So we're going to add 1/2, put a parentheses, x, which is this function right here, x minus 4, close the parentheses. I'm going to use this button right here, over 3, which brings you this. And then just hit graph, and it'll bring up the graph for your equation here. And you can hit second graph, which is the table, and it'll show you your actual plot points. Another way you can do this instead of having the actual like fractions there is you can clear this and you can do 1 divided by 2, close the parentheses, which also is the same thing as 1/2, and then put in the same thing that you had before, and then graph it. And it should come up as the exact same equation. And then you can go to second graph again, and it'll actually give you decimal points. Now that we have these decimal points, we can graph these onto our actual graph that we have here. Now we have our function on this graph, and as you can see I had to shift over the graph a little bit to get at least 3 points on it so we could graph our function. And our function looks like this here. So now we have to include the zeros, local min and max, domain, range, increasing and decreasing intervals. So to start, we're going to start with the zeros, which are also called roots or x-intercepts. we're going to look at where the function crosses the x-axis. And in this case, the function crosses right here at 4, 0. And this can also be written as like this. I'll put an R here for roots, and that's our answer. Because this is the only place where our function crosses the x-axis. To find the roots on the calculator, we can start off by going to second trace, which also above it says calc, and you go to number 2 where it says 0 and hit enter. It's going to ask you if you're left bound. You want to make sure your little X right there is to the left of where it crosses the x-axis, and then right bound, so right, and then it says guess, so you can go about where you think it is. Then at the bottom of it, it shows you exactly where your X is and what your Y is. So it says X equals 4 and Y equals 0. So that's how to get your roots on the calculator. Looking at this equation, there is no minimum or maximum because the function is a cubic equation. And also, there is no increasing or decreasing intervals since this is all just one straight function and it all just goes in the same direction. So there's no min or max in increasing interval. There is none in decreasing interval. There is also none. So now we can move on to our domain and range. Now we're going to find the domain and range for this function. So, the domain of a function is all the possible x values that our equation here can take. And the range of the function is all the possible y values. So for our example, the domain would be all reals, because although it's not shown on the graph continues to go left and right. So this here will keep going downwards and to the left, while this way goes up and to the right. And since the graph continues, the all x values can be plugged into this equation here to get a y value. So you can do an r like that for all reals. This is also true for our range for this function too. Because any x that is plugged into here will give you a y value no matter what number you plug in. So you will always have a y value. So your range is also all reals. So that's all the information we needed for this equation. So let's look at another example. In our second example, it asks, graph the function. Include the zeros, local min and max, domain, range, increasing and decreasing intervals. And our equation is f of x equals x to the fourth minus 5x squared plus 6. To graph this function, we're going to use the calculator once again. So first we're going to go back to the y equals, and you're going to plug in the equation. So x to the fourth, make sure you bring that down, minus 5x, you can use this button here for squared, shows up like that, plus 6. And you're going to hit graph to see the graph of this equation. And then you can go to a second table, and it'll give you the values for your graph. And then you can draw them onto your graph. For this equation, I didn't graph the whole entire function because we don't exactly know where the bottom of our graph is. Since on here, it shows that the graph does cross the x-axis, but we don't exactly know where it crosses since it's in between 1 and 2 or -2 and -1. So to find this, which are also called the roots, or zeros, or x-intercepts, we're going to go to second trace, which is calc, and we're going to go back to 0. Actually, hang on a sec. First of all, we're going to go to zoom and go in. We're going to zoom in right in the middle there. There we go. Now we can see that this function does go below the x-axis. So for this, to find the roots, we're going to go to second calc 0. And make for the first one, since there's 4 on this one, because the degree of this equation is 4, we're going to go left bound, go around to the bottom there, then a guess, so maybe about there or so, and it'll give you an exact decimal point for where the 1, 0 should be. And you're going to do this exact same thing for all the other points so you can have your roots, and that'll help you graph your equation. So after using second calc and finding all of your x-intercepts on your graph, you should get negative 1.7, negative 1.4, 1.4, and 1.7. And remember, you can write it like this with the fancy brackets because the y of all of these is 0. So you can just write it like this. One quick little note. If you have a function such as f of x equals x plus 4, x minus 1, and x plus 2 squared. In this, x will equal negative 4, x will also equal 1, and x will equal negative 2. But since there is a squared right here over this x plus 2 on the equation, when you graph it, at negative 2, 0 on the graph, the point will bounce on that spot, and it's counted twice. So for example, this will look something like this, where it like bounces right here on the line. It doesn't actually cross the x-axis, but it does bounce on it, and it is counted twice. Now for this equation, we are going to find our minimum and maximums. So minimum will go here, and maximum right here. So for this equation, there are 2 minimums and only 1 maximum. The minimums are the low bumps of the graph, and the max is the high bump. So your minimums will be right here, and your max will be right there. I will show you how to find your minimums on the calculator, but for this example, it is obvious to tell what the maximum is, since we already have graphed it. So your maximum is at 0, 6. And remember, that is the top point of that hump on the graph. To find the minimums, since they are not exactly on a point with whole numbers, we're going to go to second calc, or trace, and go to minimum. And it'll ask you if you're left bound, and you go over to the other side, right bound, and then take a guess about where it is, and it'll give you your exact point of where your minimum is. And you want to do that for the same thing over on this side too. To do it for your maximum, if you would like, second trace, and then maximum. And you would do the exact same thing. But for this, I would have to zoom out first. It's a little shifted, but it's okay. And then second trace, and then maximum. And do the exact same thing to find your point up here. If your point is not an exact point on the graph with whole numbers and it has decimals in it, it'll be easier to find using your calculator. So just a note, for the minimum, I also rounded up for this, and I had to extend this line here to show both of our minimum points. Alright, now we are going to look at the increasing and decreasing intervals. So you want to look at the graph and see where the graph increases and decreases. So how I always think of it is think of it like you're riding a roller coaster. In the case of our graph, you will first be decreasing until you hit this point here, and then you will begin to increase till here, decrease, and then back up to increasing. So for our, let's start with decreasing because we actually decrease first on our graph. So let's decrease. So we're coming from negative infinity. Since this graph goes on forever, we're starting with your x's. You always want to, for your increasing and decreasing interval, you always want to state your x values. So we're starting from negative infinity and going down to negative 1.6. So we're going from negative infinity, negative 1.6. And now from there, we will be increasing. So we will be going from negative 1.6 all the way up to 0. And then from up here, you put a union sign, which means that there's a break between you decreasing here and decreasing here, and that is where you increase. So this just lets you know that there was a break between there. So you'll be decreasing again from 0 to 1.6, then a union sign, and then from 1.6 to infinity, you're increasing once again. So that would be your decreasing and increasing intervals. So last but not least, we have to find our domain and range. So our domain for this function is going to be all reals, which can be written like that, and also it could be written as negative infinity to positive infinity, just like that. So that is our domain of this function, and this is because our graph will continue to go left this way on the x and right that way, also along the x, because your domain is which is the x values and your range is the y values of your function. But for this equation, our range, since we always start negative and go positive for our range, there is nothing down here, but our function starts right here, which is at negative 0.25, or as I rounded earlier, negative 0.3. So we're going to start at the lowest point of our function and go up from there. So we're going to write this as negative 0.3 to positive infinity, since this function will continue to go up. Even though it doesn't continue to go up here, on both of these sides, it does continue to go upwards. And that is all that we have for the second function here. One more thing I would like to show you is how to find an equation based off of a given graph. So there are 3 different ways to write an equation based off of a graph. The first way is y, or you can do f of x equals k x minus a x minus b and x minus c. And the a, b, and c, or more, are the x-intercepts. You can also write it as y equals k x minus a with an a up here, and x minus b. Your a and b, and if it continues more, are your x-intercepts again. And this here is how many times it bounces on the graph is, which is what I stated earlier, when a function will go like this and bounce right here on the x-axis. Another way to write this is y equals kx squared x minus a. Now this is harder to come across since your x here is going to be when 0 is the x-intercept. So these are 3 different ways that you can write an equation based off a graph. Let's look at an example. So, in this equation, there are 3 x-intercepts on this graph. So we can use the y equals k, x minus a, x minus b, and x minus c formula. And in this case, since your a, b, and c are going to be your x-intercepts, we can rewrite this as y equals k, x, and we'll start over here. This will be a plus 8, an x minus 2, and an x minus 6, since these are your x-intercepts. To find our k, we're going to substitute some other point on the curve and put that into the equation. So in this example, we're going to use this point up here, which is 0, 4. We're going to plug the 0 in for the x and the 4 into the y to solve for our k. So we will have 4 equals k, 0 plus 8, minus 2, and 0 minus 6. And from there we can solve for k. So for this, you will multiply all these together and get 96, and then you will divide 96 by your 4 on the other side, and this reduces down into 1 over 24, and that will be your k. And then you'll plug it back into your original equation, which is here, and put that in for your k. So it'll be y equals 1/24, x plus 8, x minus 2, and x minus 6. And there's the equation for this graph that we have been given. Let's look at one more example. In this graph, we have a point that bounces on the x-axis, which is right here at -1, 0. So because this bounces, we're going to use the y equals k, x minus a, parentheses a, and then x minus b. And now we're going to plug in our points along the x-axis. So y equals k, x plus 1 squared, and x minus 5. Now, from here, we're going to do the exact same thing and take another point and plug it into here to be able to get our k. So, we're going to use the 0, 15. So we're going to have 15 equals k, 0 plus 1 squared, and then 0 minus 5. And from there, you're going to solve to get k. So now we have k equals -3. And now we're just going to plug that back into our original equation, which is there. So y equals -3, x plus 1 squared, and x minus 5. And that gives you your equation for this graph. Let's look at one more example. In this case, because we have a point that crosses at the origin of the graph at 0, 0, we're going to use y equals k x squared x minus a. So we're going to have y equals k x minus 10 and x minus 16. So we don't have 0 as one of these points, because this here represents that, because if we had it, it would be x minus 0, which equals x by itself anyway, so it's right there. So we have to use another point, because we can't use 0, 0 because it's already here. So we have to use another point on this graph to be able to solve for k. So we're going to use this point here, which is 8, 6. So we're going to have 6 equals k, 8, 8 minus 10, and 8 minus 16, and from there we'll solve for k. So you will have y equals 3 over 64 x, x minus 10, and x minus 16. And that is your answer for this equation here. In this last example, this is a cubic function, and I'm going to show you how to find the equation from just this graph here. So our parent function for a cubic has the points of 0, 0, negative 1, negative 1, 1, 1. And it looks just like this. So the basic structure for a cubic function for the equation looks like y equals a x minus h cubed plus k. Let me move my calculator. Let me redo that. And k. So on the paragraph, the point 0, 0 is the point of inflection, but since on this graph here, this point is shifted to the left 4 and up 2 units. Obviously this graph is not shown, it's not drawn to scale, but it's okay. Just for this example, it is to the left 4 and up 2. Also to note with this graph, there was a reflection over the x-axis, which makes this graph negative. Since this is going up this way in the positive direction, this is going down in this way, which is negative. So it is flipped over the x-axis. There is also a vertical stretch by a factor of 3 in this equation, since the points here are 0, 0, and then negative 1, negative 1. In this, if this was 0, 0, it wouldn't, and then if it was flipped as well, it would be negative 1, up 1. But since there is no direct point right there, it's up 3 more from that. And same with this. It's instead down like this. It's not right there. It's down more. So it is stretched out by negative 3, by a factor of 3. So to put that into this equation here, the a here is the stretching or the shrinking of the graph. So in this case, it is stretching by negative 3 because this graph is negative going this way, and the stretch is by 3 points away from the inflection point. Then we have x plus 4 because the h here determines which direction the graph is going, and since it is going to the left 4 points, it goes plus 4 cubed and then plus 2, and the k here determines whether the graph goes up or down. And in this case, the graph goes up, so plus 2. And then this is your equation for a cubic function such as this. Thanks for watching. I hope you enjoyed this video and learned a lot from it.